Now, let's cover how we measure arc lengths of circle arcs. Suppose that two circles have a common center and two different radii. So I'm having two circles with a common center. So here's the first one, here's the bigger one, right? So a small and a big circle. The two circles have common center. So circles with common center would be called concentric circles. So I'm having two concentric circles. Okay. So let the radius of one of them be S and the radius of the other be R. Okay. Suppose we have an arbitrary geometric angle whose vertex is exactly the common center of the two circles. Suppose furthermore that angle cuts off the two circles into arcs M and L. So, of course, the angle cuts off the two circles, and so let's denote the first arc that's being cut off by our angle as M, and let's denote the second arc cut off by our angle as L. Then here's the claim. So here's the statement. The ratio of the two radii is the same as the ratio of the two arcs. So if you take the arc M and you divide it by the arc L, so if you take the small arc and you divide it by the large arc, you get the same ratio as when you divide the small radius S by the large radius R. I'm not going to prove this proposition. We're going to take it as is. But let's see what that proposition implies. Let's copy, right? So here's the ratio of the radii. This is the radius S, and this is the radius R. And that ratio is the same as the ratio of the arcs. So S over R equals M over L. Now, so this is true for arbitrary circles. So in particular, I'm free to choose, say, one of the two circles to have radius 1. So I'm choosing S to be equal to 1. I'm allowed to do so. It's a legal choice. There we go. S equals 1. And for purposes which are going to be apparent a minute from now, let me relabel the arc M with a Greek letter alpha. If you remember, we were using Greek letters alpha for measures of geometric angles. Okay. Next, let me massage this algebra a little bit. Let me multiply by L there, and let me multiply by R there. So L goes to the left-hand side, and R goes to the right-hand side. They swap from denominator into numerator. Okay, so I got my equality. L equals alpha times R. Now, the angle measure of a geometric angle, I want to remind you, that is the arc length cut off, not just from any circle, but from a very specific circle, from a circle of radius 1. So alpha, so this alpha here, that is an arc of a circle of radius 1. Therefore, alpha measures, so it is the measure, so alpha is the measure of a geometric angle, is the measure of a geometric have a geometric angle. Whoops. Have a geometric angle. Okay. So, let's take a look at the corollary. If I want to measure an arbitrary arc L of an arbitrary circle of radius that is not 1, all I need to do is I need to take the angle measure of the geometric angle, which corresponds to the length on the unit circle, and I multiply that by the radius of the circle whose arc I'm trying to measure. Once again, the arc length cut off by an angle of measure alpha from a circle of radius r equals alpha times r. So you need to take the radian measure of the arc and multiply it by the radius.